All right, good morning, everyone. So before we start the mini course, I just have a quick announcement. At 10 o'clock, we have the coffee break. So again, if you want coffee, you have to go to the first floor and pay for coffee. But also, we have the poster session during that time. So at the back, if you go outside of the lecture hall, up here, and then you just travel around the outside, there are posters in the hallways outside here. So there'll be the poster session outside there. All right, so it's my pleasure this morning to introduce Jialun Li, who will be talking about the entropy growth argument of Bernoulli convolution based on Hochman. Thank you.
Yes, thanks for the invitation. So today I will talk about the entropy growth argument. But this talk might be a bit too technical. So hopefully it can wake you up as the first talk. So this is one ingredient used in the proof of the dimension for, or the Hausdorff dimension of the mirror, which mentioned yesterday in Wenju's talk. So today, before introduce the entropy Bernoulli convolution, I will do some warm-up. This is the one-third contour set. So just the most simple example in computing the Hausdorff dimension of the fractal set or fractal mirror. So we take the 0-1 interval, then the classical construction of the one-third contour set. You remove the middle one-third part. Then you can, this is the first generation. Then the second generation, you again remove the one-third contour set, the part. So this is a one-third contour set. Then I will define a mirror I called mu one-third. It's a mirror. The mirror on this contour set, a probability mirror on this contour set, I call it C3. C3. And the definition is just the most simplest one. So you put, so the first, on the interval 0-1, the mass is 1. And in the first generation, in each part, you put mass 1/2. You put mass 1/2, and in the third generation, you put mass 1/4. Again, each time, if you do the division, you take the half mass in each one. You take equal mass of each one. So by this way, you can define a mirror on this contour set. So now, the first thing we want to do is to compute the dimension of this contour set. The dimension of this mirror, mu one-third. So the computation will overuse what we mentioned yesterday. It's called the property of the exact dimension. Exact dimension. And for this case, I will just do some intuitive argument. I will not give all details. So for the statement is that for almost every x inside this contour set, if we compute the log of the ratio between the mu, this mu1 bx r is the radius of the ball, and then log this one divided by log r. And then let r go to 0. So if you remember the if you remember the definition of exact dimension, it just means that for almost every x, for mu3, mu1, this kind of limit exists and gives the number of the dimension of the set. So in this case, how can we compute this number? The most simple case is that you can just take r as a special ratio is 1/3 over n. And in this case, the mirror of the ball, bxr. So it's like a ball in the nth generation. So the mirror of this set is approximately 1/2 power n. So by this way, if you take these two, then here it is equal to the exactly log 1/3 power n and log 1/2 power. And finally, you get something like log 2 over log 3. So that's some intuitive way to compute the Hausdorff dimension of this mirror, this special mirror, and it's equal to log 2 over log 3. And here, the log 2 or log 3, they have extra meaning. Log 2 is exactly the entropy in this case for some dynamic for relating dynamical system, and the log 3 is the Lyapunov exponent. So that's also like what mentioned yesterday by Fabio too. In this case, so that's a warm-up exercise. In this case, somehow this argument can be made regular, so we can compute the dimension directly from this kind of simple argument. And then let's do the real case. It's the Bernoulli convolution. So I will take some parameter lambda between 0 and 1. Then I will, so all the talk is based on my understanding, so it will be different from Hockman's original work. 1/3, then I'll try to use the language of the random walk and the stationary mirror. So we will take the random walk mu, it's 1/2 of the Dirac mass on two metrics. The two metrics are given by lambda. 1, 0, 1. And the other matrix is given by delta, lambda, -1, 0, 1. So this is like a probability mirror on the space of GL2R. Then, as an action, now we want to also introduce the stationary mirror as defined by Wayne yesterday. So when the action of the action like lambda 1, 1, it will induce now for any x, for x in the R. The action of this matrix, the map, is a fractional linear action. So it's lambda x plus 1, or plus minus 1. If you take here plus or minus, lambda x plus minus 1. So by this way, we define we have action of the JO2R on the R. So this defines action of JO2R on the R. Then we can define the stationary mirror. The stationary mirror is just the Bernoulli convolution. The stationary mirror is called there exists. It's a statement or statement. There exists a unique mirror. I call it mu lambda, such that mu lambda is stationary. It means that mu lambda is equal to nu convolution with mu lambda. So here the convolution. In this case, it can be written very explicitly. It's just 1/2 of the push forward of the first action, lambda 1, 1, mu lambda plus lambda -1, 0, 1, star mu lambda. So that's my definition of the Bernoulli convolution. To use these two metrics and to push forward these two mirrors, to push forward the mirrors. If you take the average, you get the original mirror. So that's a Bernoulli convolution, and it's like a generalization of this 1/3 contour set. For this, I will draw a picture. So first, we compute what's the fixed point of the action. So if lambda plus this one, and then you'll get x should be plus or minus 1, 1 minus lambda. So now the interval we are acting is not 0, 1, but the interval like this. This part is 1, 1 minus lambda. This part is 1 minus 1, 1 over lambda. And then the first action, the action is like lambda x. You first do the scaling by lambda, then you plus or minus 1. So after some computation, you will get the two actions. The first one will give this one. Here it is like 1 minus 2 lambda. And I checked the computation yesterday. So you will get, after the first map, the map given by lambda 1, 0, 0, 1. It will give you this one. Yeah, I think it's correct. And the other one, it gives some interval like this, starting the same point, but the end point is minus 1 plus 2 lambda over 1 minus 1. So then here appears this special number. In this question, no. So in this case, if lambda is less than 1/2, then somehow after the map, after the two maps, the two intervals, they are disjoint. So it's like a generalization of the 1/3 contour set. Indeed, the 1/3 contour set is exactly, if you take lambda equal to 1/3 and you do the scaling, then you get the 1/3 contour set. So this part is somehow it's very close to the 1/3 contour set, C3. It's a separation case. Then the question, and in this separation case, we can compute the Hobsbawm dimension exactly by the same formula. Entropy is log 2, and the Lyapunov is log 1 over lambda. So now the question is that if lambda is greater than 1/2, then what happens? Well, what can we say? Question is understand what lambda greater than 1/2. The dimension, Hobsbawm dimension of this mu lambda. How can we compute them? And this question has has some history. Like there are some conjecture by Edosh. The conjecture states that if lambda is not some special number, if lambda is not piso, then mu lambda is absolutely continuous. Here, absolutely continuous is something stronger than dimension 1. Just means the mirror has some density. Yeah. Here there is a condition that 1 over lambda not piso. So here piso is a special condition. Piso number. It means that I call it alpha piso. If alpha is greater than 1 and or is Galois conjugate. Has absolute value less than 1. It's some special algebraic number which has a very good property. Less than 1, yes. So that's the conjectural Edosh. Because if 1 over lambda is piso, then there are something different happens. If 1 over lambda is piso, then somehow we can prove that the Fourier transform of this mirror, if you take some frequency, it will not go to 0 as k go to infinity. So piso number, once it's 1 over lambda piso, then something different happens. Since the Fourier transform of this mirror doesn't go to 0, so it cannot be absolutely continuous. It's like from the Riemann-Lebesgue, classical Riemann-Lebesgue lemma. And moreover, in this case, we also know, in this phase, another factor is that the dimension, the Hobsbawm dimension of this mu lambda will less than 1 for the piso numbers. So then what about, then we come back to the question about the computing Hobsbawm dimension. What about other parameters? Can we compute the Hobsbawm dimension? Is it equal to 1? So then it comes the work of Hockman. who invented a new work, who invented this entropy growth argument. So I will state the countable many, yeah. Countable many, at most countable, because it's algebraic numbers, they're at most countably many. Which conjecture? The two of them, yes, there are a lot of history. I try to skip a bit here. For example, for first one, the absolutely continuous, there are work by Solomiak and Hockman. Oh no, Solomiak and Schmekin. In this conjecture, there are Solomiak proved that almost every lambda is absolutely continuous. Schmekin proves that for lambda which is not absolutely continuous is a Hausdorff dimension 0. And for the dimension thing, I will mention later. So I will just going to state the theorem of the Hockman. Yeah? Yes? It's the big mirror. It's just the big mirror because it's just. Rational number greater than 1, yeah, it's also piso. No, rational number. Yes. Yeah, it's piso, yeah. Yeah, I think so, yeah. 2/3, it's, let me see, 2/3. So the result of Hockman. It simply states that dimension or the Hausdorff dimension of this Bernoulli convolution mu is equal to the minimum, no? And to add some condition like lambda algebraic. Just for simplicity, the theorem is more general. It assumes some exponential separation condition, but if lambda is algebraic, it's always true. It's minimum of 1 and h lambda over the 1 over lambda. So here again, it's this h, I will define h lambda later. It's some entropy. And log 1 over lambda is actually the Lyapunov exponent. So it's like similar to the classical form commutational Hausdorff dimension. You always entropy by the Lyapunov exponent. But since here, the total space is dimension 1, so you must take a minimum with 1. So that's like a theorem Hockman. And here, there are some definition of this h lambda. H lambda is like called the random walk, and it's, let me state, it is a random walk entropy of the random walk nu. And the random walk entropy is defined by the limit n go to infinity. You take 1 over n. You take the Shannon entropy of new convolution n times. So again, another definition is that H is called the Shannon entropy in this case. And no, I just read here. So if M is some like finitely supported mirror, then HM is defined by the sum of the atoms of the log. Oh, no. It's MXI, log XI, where XI is in the support of M. Yeah. So that's the that's a definition of this Shannon entropy. Just for any finitely supported mirror, you define its entropy by the most classical way. You look at the atoms, and for the mass of each atom, you use minus mx times log mx. This is H, and the random walk entropy is that you take the convolution of nu n times. So you get after convolution, the matrix become more complex. You have a lot of different matrices but still it's finitely supported, so you can use this h, and then you divide by n. The limit exists because of some classical thing from this entropy. You have sub-additivity, then you have a limit. This limit is called the random walk entropy, or this random walk nu. And in this particular case, it's one parameter, so we call it h lambda. And also there are some precise thing is that here this log is always log 2. I think so, yeah. Yes, we'll take log, we'll always take log is base 2. So now I will try to explain the main idea or the proof behind this theorem. And before going that, so just check this formula. If lambda is equal to 1/3, so the 1/3 contour set, then this h lambda is just log 2. Oh no, I'm wrong. Here is not. Oh yeah, no problem. It's oh no, it's fine. Here is since 1/3 is somehow the random 1/3. In this case, this 1/n h new convolution n times, it will always equal to the 1/n, and this, because somehow in this case it will generate a free semigroup, so the entropy here is exactly n times log 2. So the entropy log 2, and the Lyapunov exponent is log 3. So it recovers the classical computation of the 1/3 contour set. But it's much general because it covers the case lambda greater than 1/2. So how can I compute this dimension? The motivation is from this, the property dimension is the exact dimension. So the first thing is we recall. It's some result of Dejun, Feng, and Hu. They prove that this mu lambda, they are exact dimension. And then something mentioned yesterday by Wenyu, but didn't state it. Now I state here. It's something from real analysis. It's a result of Yang, Lai-Sang Yang. It states that once a mirror is exact dimensional, then you can compute the dimension from the entropy. The dimension, Hausdorff dimension of mu lambda is given by limit n go to infinity, 1/n. The entropy of mu lambda with respect to the some partition Qn. So here, this is another entropy different from the Shannon entropy for discrete case. Here Qn first. Qn is a partition. Partition. It's a two-adic partition. So more precisely, the atoms in Qn, they are by this way. Qi. Each atom is like k over 2 power n, and k plus 1, 2 power n. So it's left closed right open interval or length 1/2 power n. This is the atoms, and it's the partition is the partition of the real numbers. The entropy here, the entropy mu, with respect to this one partition, is defined by something similar to Shannon entropy, but you replace the atom by these atoms. So it's the sum over k, sum over I, in this Qn, minus the mu I, log mu I. So that's a definition of entropy. Here is this one. Yeah. Yes. F, yeah. No, this one, by this sense. Since it's exact dimension, so we have this formula. So here, I try to give a bit more intuition. So here, why is the exact dimension that tells you this entropy? By computing this entropy, we can get a dimension. This is because that this mu I, each mu I, it is more or less like from, if we assume the convergence is like the exact, so each mu I is like 2 power 1 over 2 power n times the dimension of mu. Then if you take the log, it's more or less the n times the dimension of mu. No, there is n. 1 over n, yes, correct. And times log 2. Log 1/2, something like this. So if you replace log mu I by this formula, something like dimension mu, can you see it? Too low, yeah. It's too low. If too low, yeah, I can write there. Yeah, I can write here. So here, by exact dimension implies this. This mu I is more or less like something 1/2 n power the dimension. So then your log mu I is somehow it's like n dimensional mu times log 1/2. Then if you compute the sum of this minus mu I, log mu I, somehow it's mu I times n dimension mu, log 2. So if you compute this one, then since the sum of mu I is 1, so you get something like n log 2 dimension mu. So this gives you some intuition about this computational entropy. It can really give you the dimension. But it's a bit tricky one. So you need to replace mu I in the log by something given by dimension. But outside, you just sum up as a probability measure. Then, what's the advantage of replacing the computation or dimension by computational entropy? The advantage, as my understanding, is that for entropy, you have much more tools. Like what we will play with later is like we'll try to use different scale. We'll introduce the conditional entropy later, and we will also use the convolution in this part. So it gives you more, it's like a function, gives you more tools to deal with than just a number of household dimension. Yeah, so the starting part, the proof, yes, so let me try to give the step 1. Now I'm trying to give some idea of the proof, the step 1. So what can we do with mu lambda? There are not so many things. There one thing we can do is use this stationarity. By stationarity, we know that mu lambda is equal to mu convolution n times then convolution mu lambda. Yeah, that's Hockman's proof. Yeah. It's proof. Thank you. No, it's the proof idea. I think the rest part is all about the proof. So the first step, I try to use the stationarity to get some information, get some more things. Question before the proof. Yes, I read this part. So log 3, yes. Yes. So here we don't have many choice. So the first step is just try to use stationarity to rewrite the measure as a convolution. Then observe that this one, the atom, its atom is like lambda power n plus minus 1 plus minus lambda blah, 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 lambda n minus 1 and 1, 0, 1. So the atom is like this. So it means that the action of this matrix on the real line is first by contracting with this ratio, lambda power n, then do some shift by this measure. So in order to use the information of this contraction, we will introduce another scale. The scale is called another scale. The scale is n prime. Now define n prime as the integer part of log 1 over lambda and n. This will be another scale. This scale is like the lambda power n scale. And then then another thing, we want to use scale, so we need to introduce another thing called the conditional entropy. Because the scale, this scale is, scale n is somehow not useful for here, this conditional entropy. If you have two different scales, like m greater than n integers. And then we can define the conditional entropy H mu Qm with respect to Qn. This conditional entropy is defined, there are two ways. First, it's just the difference of the entropy at different scale. And on the other hand, it can also be written as the sum over I over Qn, mu Qn, mu I. And the condition, the entropy of the mu I with respect to Qn. Mu I is the rescaled measure I will define here. Mu I. Mu I is just 1 over mu I. The mu restrict to this I. So we restrict mu to the atom, then we divide by its total mass to get a probability measure. So that's like the two definitions of the conditional entropy. And the advantage of doing this is that now we are going to some smaller scale. And you can do something more. So this is the first step. Yeah. Then I will take another parameter. It's just some q greater than 1. Now I will try to do some computation, and from this computation, we will see where does the entropy growth argument comes from. So first, I try to compute the conditional entropy of this measure mu with respect to this Qn plus n prime, Qn prime, 1 over Qn. So you will see later, this choice is particular, but it's very useful. This kind of two partition, Qn plus n prime and n prime. These two, it will appear later. So first, by the definition of conditional entropy, you can write as the difference. So just the Qn, H mu, Qn plus n prime, minus H mu, Qn prime. Now what can we, now as n go to infinity, now as n go to infinity, what can you guess? It's now, as n go to infinity, we can get the dimension of mu because of the exact dimension of the, no, I erase that one. I need to rewrite here. It's like one of the most important thing here. We will use this one several times, the Hall entropy, or the mu Qn. as n go to infinity. This one is equal to dimension of mu. Yes. So applying this for this limit for this difference, we find that the first one is the partition of scale qm plus n prime. So you get the dimension mu times qm plus n squared. And the second one is like n prime times the dimension of mu. So the difference exactly gives you the dimension. As n go to infinity, the limit is dimension of mu. It's fine. So you just use that formula. So use the limit. You can get that this difference is dimension mu. Then we have another way to compute this conditional entropy by the second formula. So then we will use another thing. Yes. So the second way. That's the first way. The second way to compute this quantity, Qn h mu lambda. Now erase, no, I didn't write lambda, so Qn plus n prime, summation Qn. So by another definition of the conditional entropy, it's just the sum over I in the atoms of Qn, and Qn is here. There are two. Qn prime, it's a Qn prime. Then you are computing this mu I and the entropy of mu I Qn prime. Now here I want to treat a bit. Indeed, this mu I, in this case, this mu I will be very, very close to another measure. It's mu convolution n times I, convolution mu. So let me give the definition. So then we want to replace something. First step. Just erase this thing. Just erase the thing I want to erase. I want to use it. It's new convolution n times mu. So what's the definition of mu? This one. Mu convolution n I. In order to define this, I need to make a map. The map phi is from this ABC to its B part. This is the map. And the mu I is defined by the new convolution n times phi inverse I, and the new convolution n time restrict to I. So that's the definition of nu I. And the property we used here is just mu I. So that's a definition of in some restriction and rescaling of this new convolution n times. Then this mu I, by stationarity, is just the new convolution n times convolution mu. Then you try to go to the atom of I. And somehow this one is very close to this. So I treated a bit, but it's very close. They two, by some ways, they are some like similar. Or phi inverse I. Yeah. So here is also the place we use the stationarity, because we want to use stationarity at some point. Otherwise, we don't use a lot of information of this measure. So there's a place to use stationarity, and somehow we can replace this mu I by this convolution. So let's do it. With some controllable error, we can do this. So it's 1 over Qn. Sum. Still, this one will be replaced by something, but now I need to treat a bit more. It's mu I. It's something, yeah, something like this. Here it's mu I convolution n times. Yeah. Yes, now, the advantage of all this computation is that we get something with convolution. That's where the entropy growth argument happens. It always happens as this kind of convolution. So for this kind of convolution, you can, first we try to estimate trivially, then we get something. We get some like thing similar to equality, then we will see it cannot be. Yeah. Yeah. Because I just want to define. Indeed, I can also define this partition in the level GL2R, but it's too complicated, so I do this ad hoc one for this new. Because if you want to do entropy, yeah. No, it's not what kind of words. It's more like after all this composition, where lies this matrix? So it's like because because A part is always the same if you look at the atoms in the new power n, new convolution n. So only difference is B part. So then the partition so the partition only need to define the B part. So it's a way to define it, but it's not standard. Yeah, then the most important part is this convolution. There is like trivial inequality. Trivial one is like this. The trivial one is just the new I. Just if you have two mirrors, you take the convolution. Then you can, it's always greater by convexity argument, it's always greater than the second one. You can just replace, ignore one, Qn plus M. And minus some error, but something reasonable. So that's the trivial one. So if we do this trivial one, then starting from this one, it's called the star. I call this formula star. So then star is greater. Star is greater than sum over this i's, Qn. Yes. Yes, there are some terms like this. And then this one is just mu Qn plus M prime. Did I do something wrong? No, I do something wrong here. Here we need to be more careful. Yeah, I do something wrong. Sorry. Yeah. Indeed, this one you need to divide again. So here is this convolution not good. But this one is not correct. It's an additive convolution is good. So this one indeed is equal to the new convolution and I delta 0. There are some translation part, as I mentioned, there are some translation part and then scaling part. So I forget this scaling part, there's something. I just erase, just redo the things. So recall this, the application of this ABC01, or X is given by AX plus B. And here we try to replace these two parts. This is a scaling part. This is a translation part. So S lambda n is a scaling part. S lambda nx is equal to lambda nx. So we separate the scaling part and the shifting part. The shifting part B is exactly given by the action at delta 0. Delta 0 is atom at 0. And this plus is the additive convolution inside R. because at the beginning, this convolution star is the action of the group, so it's not that good. And now we try to separate the information to two parts. Then we can use the what I said, the trivial inequality to get this one. To get this one, this h nu I convolution n times convolution delta 0, and plus this one. Qn plus m prime. Now we can, because this part is just a shift, so we can forget this one and just use the second one. Then it's just a scaling. And for computing the entropy, the scaling, if you here do this, you can here the scaling, so you can do the expansion. You can expand here you can also expand the atom. And with by some scaling invariance, you can forget this one, you get Qn. Yes, it's Qn. So now if we come back to here, we will get some trivial inequality. Last line. I can write here. It's a great, at the end, what we get is h mu Qn. This one. Because you forget the shift part, then you do the scaling. You use the scaling invariant to get this part. This step is something standard if you know the entropy computation. Yes. Then we can come back to this equality, this one. Then this one is greater than 1 over Qn, the sum over nu I and I, and the entropy mu Qn. Now again, as n go to infinity. Now we will use this inequality again, this limit again. If you let n go to infinity, then you get Qn. This sum over I is just sum 1, so you get Q and Q times the dimension mu. And the dimension. So after all this computation, for this star, we have a two way to compute it. And one way tells us the limit is equal to the dimensional mu. And the other way tells us the limit is greater than dimensional mu. So it means that this equality, this tells us that this equality must be something like this one. This one is the important part. So it tells us this equality, somehow it should be almost equality. Inequality should be almost equality. So that's the starting point of the entropy growth argument. Indeed, if you add some assumption, not this one, but this, this one, this one. So this is the most important equality. So indeed, if you want this convolution is almost equal to this entropy, it will impose a very strong constraint on these two measures. So that's the starting point. Then we can state the entropy growth theorem of the Hockman, and it can finish the proof. Yeah. So what I mean is that if this star inequality is almost equality, then the two measures must be very special. In general, we should get some entropy growth. So this theorem of Hockman. If you have two measures, eta 1, eta 2, on R, and satisfy some conditions. The first one is that the support of eta 1, eta 2, somehow they are out scale. And there are some scale analysis, but they are on something like C 2 power minus n. Okay. So the statement is for any epsilon positive, there is some delta, and C. There is some delta positive, such that the following holds for any measure like this. If their support is of size 2 power lambda minus k, and the first one has some positive entropy, Qn plus k, 1 over n. It is greater than epsilon. And the second measure satisfies some thing called the epsilon entropy porous. This one I try to explain later, like maybe tomorrow a bit. Then there are some. Then if you compute the entropy of the convolution, eta 1, additive convolution eta 2, with respect to Qn plus k, this one should be greater than one over nh, the second one, Qn plus k, plus the most important delta. Yes. So that's the entropy growth statement for any two measures on R, probability measure. For any two probability measures on R, k just as some scale. You can think about k equal to 0. They are supported on the atom near 2 power minus k. Then you're going deeper to scale n to see some entropy of the first one. And for the second one, there are some entropy porous. It's like at some scale they have some. They are not dimension 1. At some scale, you have some place to add things. So it's intuitively this, but the exact definition is a bit complicated. And then once you have these two things, first entropy, positive entropy, second entropy porous, then if you do the convolution, then you will always get entropy growth here. So now this plus is like the additive convolution because I already used for other notation. It's just additive convolution. In R, you have the additive structure, so you use additive convolution. Yes. So I think. So in last few minutes, just try to state the main argument. Then the main argument of Hochman is given by using the proof by contradiction. So now suppose step 2 maybe like. Suppose the dimension of mu is less than the minimum of 1 and h lambda divided by the Lyapunov. H lambda divided by Lyapunov, then two things will happen. So this by now proof by contradiction. Proof by contradiction. So suppose the formula doesn't hold. So the dimension is smaller than the expected one. Then this one. The dimension mu less than 1, it will imply the second condition. 1, 2, 3, 4. Yes. It will imply the third one. No. I still need some statement. Yes. I state here. Yes. Step 2, yeah. Proof by contradiction. Then we will use the theorem with this eta 1 is just this measure. Eta 1 is this one. Mu I convolution n times. And eta 2 is the second part. It's lambda and mu. Yes. And the scale k will be the n prime. and the n will be the Qn. So we will apply the theorem to this inequality, to this part, but the choice of eta 2, eta 1 is just given by here. This is eta 1, this is eta 2, and the scale is Qn plus n prime, this is n plus k. We'll apply in this case then. Then if we want to apply, then we need to verify the condition. So here it comes from the conditions are verified because you have this contradiction hypothesis. Indeed, this dimension less than 1 tells you that the third one is verified. And the dimension less than the entropy divided by the Lyapunov, it will give you the second one. It's like the arguments. Then, so still have 3 minutes, so I can try to explain how do we use this this part? How do we use this part to get positive entropy? It's a similar argument as this conditional entropy, but now we replace this one with another measure. N times delta 0. Yes, I just tried to do this one. Yeah, now I want to try to explain how do we verify the second positive entropy condition. So it's some game similar to your, yes? What? Oh, yeah. I need, no, because, yeah. Because I assume lambda is algebraic. So in fact, it will appear later here. It will appear here. Yeah. N is Qn. No, here in the, you mean here? N is Qn. Yeah, here N is Qn because divide by Qn. I always divide by Qn. So it's N is Qn. Yes. K is n prime. Yes. So the verification of the second part, the positive entropy part, is somehow similar to the previous computation. It's also try to compute this conditional entropy in 2 ways. Then get the positive entropy. Yes, one, yes. And here you can get something just like this. And this one is new convolution n times Qi. The positive entropy is for eta 1. Eta 1 is delta 0, yes. Delta 0. Yes, no, I don't need this one. I just use this one. So first, you can use the definition of the conditional entropy. Just get the sum of this kind of type. Well, the second condition is like we need some positive entropy for this kind of things, for this kind of entropy. But then the conditional entropy tells us if you want to prove some portion of this is positive, then you only need to prove this conditional entropy is positive. Then for this one, you have another way to compute. That's the last part. And here comes the separation. Minus Qn. N prime is. Now, by definition, you can write it as a difference. Now we compute the difference separately. For the second, I just need some place here. Yes. At first, I compute this one. This one is simpler. This one somehow, this is like n. It's an approximation of mu at level at the difference of lambda power n. So this one is approximately the mu Qn prime. Then we can use this famous equality limit here. So this one is almost like n prime times the dimension of mu. This is the second term. And the first term is the most important term. Here we use the exponential separation. Qn plus n prime. Yeah. Here, because this Q is a parameter very large parameter we can choose at the beginning, which depending on the separation condition. So by choosing this Q very large, we can suppose that there are no two atoms of mu power n, mu convolution n lie in the same pattern, in the same atoms of this size. So this here is exponential separation. So you can replace this one just by the mu power n, Qn. Yeah, it's really using the exponential separation. If you take Q very large, this parameter Q very large, then somehow computing this entropy just try to computing each atom, the atoms of mu power n. So here we replace the entropy respect to this partition to this Shannon entropy. It's coming from this exponential separation. Then this one, the limit is the h lambda. So it's by this way we can finish. Because now, if you compute the limit, the first term is somehow by h lambda. Second term is dimension mu. Now we suppose this dimension mu is smaller than something. So the difference will be positive. So that's where it comes from the positive entropy. Thanks.
All right, thank you. Are there any questions? Amy?
Yes.
Just so I understand, you use the algebraic property in the exponential?
No, it's just here. In fact, this one is not critical. It's the actual statement is more general here.
I see. You don't need that. You need what you're calling exponential separation, which has something to do with being one atom in each element of the partition.
Yeah. It's, here it means there exists some C, there is some C positive, and for any xy in the support of mu power n, the difference of xy, the distance between xy is always greater than exponential minus Cn. It's this kind of condition.
Can you explain why that holds for algebraic?
For algebraic numbers, it's because algebraic numbers are more separated. Right? You can just think about the rational case. So if two rational numbers, like x, y, they are rational. Rational, like with denominator, with numeric denominator. Later, like 1 over something like p power n. With denominator p power n. Then if they are different, their difference is greater than 1 over p power n. So that's so in this case, it's easy to verify this separation.
Thanks.
Other questions? Oh, yep.
No, the algebraic is only used this here. Here, so it's. In this case, for Bernoulli convolution, it's a result of Peter Varud after, and he proved that for transcendental lambda. So if lambda not algebraic, it's transcendental, then the dimension, Hausdorff dimension, is always 1. So it works. It works. Indeed, it works. There is some modification. No, it's a bit different. It's more like you, in some step, but the story is just here. So here, it's just you want to compute this one from this one. Then you need to do something. It's this step, like Varud did something to approximate now like transcendental parameters by some type of algebraic numbers. It's this part. It's only this part you need to modify for transcendental one. The previous is all general. More general. Yeah. Yes. Yeah, I think there are a lot of conjectures, but here is the most basic case. It's a self-similar case. Once you go out of this self-similar case, you need to do so it's like what we did in this as a projective linear case, SO3R case. You need to do a lot of linearization, and also the entropy computation is much more difficult. I think it's possible to generalize some to a bit more general situation, but it will be complicated. And also the, no, I don't. Yeah, there are a lot of conjectures on this dimension here. It's always like entropy divided by the half-stop dimension, especially here the difficulty is coming from there are overlaps. So.
All right, maybe in the interest of not cutting into the poster session too much, we'll finish up here. So thank you again, Jialun.